Hey, good Wednesday morning, everybody. Welcome back. Hopefully, you had success working through the first two topics in Chapter 12, 12.1, 12.2. And today we're going to finish off Chapter 12 with our third and final topic. And as I said, these are pretty short and easy, as you'll see again today. So a quick review. We started off Chapter 12 looking at reaction collision theory. And that meant understanding what it takes for a successful reaction at the atomic level. And the first thing was that in order to have a reaction, you need to have a collision. And when you have a collision, the molecules have to collide with two key criteria. Do you remember what they are? Speed or kinetic energy and orientation. Good. Okay. Now, if they have enough speed and they collide at the correct orientation, then you have the opportunity to break bonds, which is required to make new chemical compounds. So bonds are broken and bonds are formed. And the energy that is required to break the bonds and released when the bonds are formed is called the bond energy. And we looked at bond energies yesterday. We looked specifically at how bond energies affect the enthalpy of a reaction, how they're connected to the activation energy. So I'm just going to do a little sketch diagram, and we're going to go endothermic. And here's our delta H, products minus reactants. And if we add an energy pathway, then we call this the activation energy, and that would be the energy required to break bonds. And this would be the energy released when bonds are made. So if we wanted to calculate the change in enthalpy, we could also go breaking minus making, and that gives us the same value as Hess's law of enthalpy of formation of products minus reactants. So today we're going to look at catalysts. So a key idea, catalysts are not used up in any chemical reaction. That is very important. They're not a reactant and they're not a product. Okay, they are not consumed. You get them back at the end of the reaction. So what is the purpose? How do they work? And what industries use catalysts? So that's what we're going to be looking at today. I'm going to jump backwards in the lesson a little bit. And we're going to take a look at a potential energy diagram. And usually we see the energy pathway as the black line. This is what we've been talking about the first 2 days. Okay, so we've got our reactants, we've got our products, we've got our delta H, which we could calculate here. Products minus reactants. The products are at 50 kilojoules. And the reactants are at 100 kilojoules. So 50 minus 100 is negative 50. Okay, so this is exothermic. We've lost 50 kilojoules. That makes sense. We've dropped down 50 kilojoules. Now, you guys learned about energy of activation. Oh, that is messy. Okay, so here it is, the energy of activation. And in this example, we had to add, we went from 100 to 180. So we are adding 80 kilojoules of energy to get this thing over the energy hill. And that is energy that is being used to break bonds or activation energy. And then it falls down the hill and releases more energy than it gained, giving us our exothermic reaction. So catalysts are an entirely new pathway, and that one is drawn in red. So if you follow our red pathway, we start in the same spot with the reactants. We finish in the same spot with the products. Our delta H catalyzed is the same. It's the same products. It's the same reactants. So that doesn't change. What does change is the activation energy. So you need to add less activation energy with a catalyst to get the reaction started, but it doesn't change the overall enthalpy. So how do catalysts do this? Well, here's one model from biology. And what it's showing you is the catalyst in green has a unique shape. And this shape allows the two reactants to collide with the correct orientation to make a bond. And if they are colliding with the correct orientation, you need less energy to get a successful collision, and therefore you get a reaction with a less activation energy, but the overall enthalpy of bond breaking and bond making hasn't changed. Okay. Here's another view of looking at catalysts. This one's a little more complicated. If you look at the uncatalyzed pathway in black and the catalyzed pathway in red. So still true that the catalyst lowers the activation energy, so significantly less. And how does it do it? This model is proposing an alternate pathway. In red. So what's actually happening is there are several intermediate steps or activated complexes. I'm just going to put, there are many activated complexes and they all have a lower energy of activation. So an alternate pathway in this one, it was actually what you were seeing in the demonstration in yesterday's class where you watched the video of the solution changing multiple colors and producing gases and changing temperature. So this could have been color 1, gas bubbles produced, temperature shoots up, color number 2. So these were all intermediate reactants and products as we moved from XY to Z. Okay, so that's some pretty heavy theory on catalysts. Now let's sort of look at the practical side of things. Whoops. So in your notes, in your study guide, page 141, you can fill in this slide. I'll just let you pause it for a minute to copy down what you need to fill in your notes. Okay, so catalysts lower the activation energy by providing a platform or a surface, which encourages the reactants to collide at the correct orientation. And this greatly increases the chances of forming an activated complex, which equals a reaction. So the rate is increased if the chance of a successful collision is increased. A tiny amount of catalyst can greatly increase the reaction rate. It's literally drops. Catalysts don't wear out. They don't take, aren't consumed in a reaction, but they do need to be cleaned up or purified. They do get damaged or dirty. And we already talked about this key idea. Okay, so a question for you. Will a catalyzed reaction occur at a lower temperature than an uncatalyzed reaction? And the answer is yes, due to lower energy of activation. All right, so we're back to your notes again, page 141, and it talks a little bit about catalysts in industry. So catalysts can speed up the rate of a reaction and save time. They can lower the energy of activation, save time or energy, and you save money, which is huge in industry because industry is all about generating profit. And catalysts are a multi-billion-dollar business, the field of catalysis. So chemical engineers study catalysts and they work on developing new catalysts all the time for lots of different types of reactions, including all of these ones, which we looked at in organic chemistry. Another interesting example is catalytic converters that are found in the bottom of your car in the exhaust system. When car engines burn, they also produce, they combust a little bit of nitrogen to make nitrogen monoxide or nitrogen dioxide, which can then combine with water and make acid rain, HNO2 or HNO3. Not good. So what a catalyst does is it lowers the activation energy for the reverse reaction. so that before the nitrogen monoxide leaves the exhaust, it is converted back into nitrogen and oxygen, decreasing the effect of acid rain. So every car manufacturer today is supposed to have one of these guys in the exhaust system to reverse that reaction and decrease the acid rain forming gases. Okay. By the way, those contain a heavy metal that's worth a lot of money, and people have been stealing them recently, literally climbing under vehicles with a hacksaw, cutting them off, getting the platinum metal out, and then selling it on the illegal market for lots of dollars. I think to replace your catalytic converter on your car can be anywhere from $400 to $1,000. So that sucks. Okay, some examples in petrochemical industry of catalysts. So zeolite is an alloy, platinum, rhenium, sulfuric acid, hydrofluoric acid, palladium. So we've got some metals and acids, and these are all used for different processes, industrial processes in the petrochemical industry, and they're all about generating valuable products which are worth a lot of money. And I found this to be a very interesting did you know. Before we had the modern catalysts of today, you could only get about a quarter of a barrel of oil converted to gasoline in the 20s. And with modern catalysts, we can now convert about half of a barrel of oil into gasoline. So that is literally doubling the octane component of a barrel of oil with catalysts and catalyzed reactions. Okay. From a biology perspective, catalysts are called enzymes. So a catalyst in a living system. So you're all familiar with enzymes. These are protein molecules that also control reaction rates in living organisms. It says here, great many physiological reactions such as metabolism are controlled by the amount of enzyme present. Okay, they're also used in the food and beverage industry for cleaners, pharmaceuticals. They have all kinds of uses. And the lock and key theory is one example of how an enzyme produces a correct orientation. And if you get the correct orientation, you can lower the activation energy. So again, here we have another example of a catalyzed and an uncatalyzed pathway with two different activation energies. It doesn't matter which pathway you take, the delta H is still the same. Products minus reactants, 30 minus 70, or negative 40 kilojoules exothermic. If we were going forward, reversing the reaction so that this was reactants and this was products. Products minus reactants for the reverse reaction, delta H reverse, would be 70 minus 30, which is plus 40. Hopefully that makes sense to you that when you run the reaction this way, it is endothermic. It is going uphill like that. Okay. Examples of enzymes as catalysts in industrial and living processes. So household detergents have catalysts in them to break down all the food products that we get in our clothes, so proteins and fats and oils and starches. The brewing industry uses zymase, which is found in yeast, to convert sugar or glucose into ethanol. Cleaning your contact lenses, you add an enzyme, catalase, which decomposes hydrogen peroxide to oxygen and disinfects your lenses. Oh, there's all kinds. You can read the list. So different types of enzymes for breaking down sugar. You'll notice all the enzymes end in A's. So in biology, anything that ends in A's is an enzyme. Another one. And then chlorophyll in photosynthesis. So lots of examples. And you can put some of those in your notes if you would like. On page 142. Okay, last slide, and then I've got a couple videos for you guys. So this is sort of the mechanics at the atomic level. This is an uncatalyzed reaction of methanoic acid decomposing. And if you remember, methanoic acid is HC double bond O, OH. So HC double bond O, OH. In order for methanoic acid to decompose, two molecules have to collide at the perfect orientation with enough kinetic energy to slam together, break bonds, and make bonds. And as you can see, that you get this potentially activated complex forming, which then decomposes, spits off a water molecule, an H2O, and a carbon monoxide. It's slow, and it's random, and it doesn't happen very often. Okay, so, by the way, why does this thing decompose? You'll notice that in the collision that one of the hydrogen atoms got moved, it's this guy, gets moved from the carbon onto the oxygen, which makes it unstable. And an unstable activated complex with high energy falls down the energy hill and decomposes into stable products. All right, this one was untouched by the reaction. Its hydrogen atom was not rearranged. So in a catalyzed reaction, this is using an acid catalyst, and an acid catalyst has a free proton. The proton can combine onto the water molecule, making it unstable, like above. And when it's unstable, it will decompose, the water falls off. Now we still have this unstable product. It will become stable by losing the proton right there and turning back into carbon monoxide. So water, carbon monoxide, and our catalyst is returned. You always get the catalyst back. So in this case, the H plus that we started with, we get it back. It's not the exact same H plus, but it's still a proton, and a proton is a proton. It doesn't matter if it was the one that was, let's see, if we trace it through here, it was this guy. So that proton became this one, and this proton became this one on the water molecule. It's fast and it's organized, and this is what speeds up the rate of the reaction for catalyzed. Okay, so now I've got a couple of videos to show you. This one is just for fun. This is a catalyzed reaction with hydrogen peroxide, and it's called elephant toothpaste. Oh, wow, how about that? Let's try it again.
Do the hand off. All right.
Hang on 1 second. Let's make sure I have mine ready, because once we do this, there's no stopping. This is kind of a one and done kind of
One
thing.
and done. This is the only shot.
Two. Sarah's got two. You've got two. You know
All
what?
right.
These are a little bit. They lost.
Top me off there.
Top you off with extra catalyst. Okay, I'll get rid of that one. All right.
Okay, send down the mic now.
All right.
Okay.
So nothing's happening in these reactions until the catalyst is added.
3, 2, 1, pour. Step back. Hey!
Yeah. All right. So, again, 35% hydrogen peroxide. We're using sodium iodide to catalyze the reaction. We added some food coloring. All those bubbles are filled with oxygen gas. It's just a classic.
It's a brightly colored mess. Take a look at the two here. Hopefully this will be cleaned up by the time you head on down to the imagination station.
I'm sure a little rain will come by.
Okay, second video I'm going to show you guys. I'm just going to show you the start of it. I'm going to put this link in my website. This is the lab we were supposed to do. If you were in class and I was in class, we'd be going on doing this one in our lab. So it's called the iodine clock. It's a pretty cool reaction to see. And unlike this video, he varies concentration, but we would be varying the amount of catalyst that we add to change the pace of the iodine clock.
This is one of my absolute favourite chemistry demonstrations. You might think, in an age when we're used to seeing all sorts of special effects on screen, something like this might have lost its impact. But there's a world of difference between cheesy video effects and seeing something in person. Demonstrations like this can be part of a lesson.
Okay, and so I would like you to watch this video. He's going to manipulate some variables and show you some different ways to set up the iodine clock. And then if you are fortunate enough to have some ingredients at home, you can make your own iodine clock, and I'll provide the link to this video as well. Okay, so I'm not sure if you have potato flour. I'm not sure if you have hydrogen peroxide or iodine. If your parents are really well stocked, you may be able to pull this one off. And if not, my apologies. I really wish we could do the iodine clock together at school. It's one of my favorites. Anyway, I'll provide these links in my lesson. And back to... So where do we finish today? You've got one good review page in your guide, page 143. It kind of summarizes 12.1, 12.2, and 12.3. You've got some textbook questions that you can work on. Tomorrow, Thursday, is going to be like a review class, and you will be given time to work on the graphing assignment that I am hoping to collect from you at the end of the week, and work on that iodine clock if you have the supplies. And I'm hoping that we can try some type of an online quiz. I'm just starting to experiment with some of the quiz software that's out there, and I want to do some trial runs before we do any kind of real assessment. So that's coming up. Okay, so work on number 1, number 2, please. And again, email me if you have any questions. Okay, take care, everybody. And I'll talk to you tomorrow.